Good morning. We begin lecture 47. We are coming towards the final lecture of CDMA on the topic of CDMA. The three main takeaways that I would like you to focus on, in addition to the various pieces of theory regarding the sequences, regarding the aspects of spread spectrum, are the following. How does direct sequence spread spectrum / CDMA systems, how do they handle multipath? That's a very, very important element. That's what we have started in yesterday's lecture. That's what we will begin to study today. Then we also said that the strength of the CDMA system is that it is robust to multi-user interference. So how does it handle multi-user environment? So multipath plus multi-user is the system environment in which we are working in. And what is the capacity that you can achieve with the CDMA system? How do we characterize it? And how does the cellular system take advantage of that? So that is the goal. These are the main things that I would like you to focus on as takeaways. But today we build on the framework of a multi-path environment. So by way of a quick summary of lecture 46. Lecture 46, we spent some time understanding the Gold-Kasami sequences. So the key points are that Gold and Kasami, sometimes called Kasami Gold, basically this is the early work in the late 60s. They came up with pairs of sequences called the preferred sequences. The preferred sequences had the property that they had a 3-valued correlation. And all 3 values were good values. So that means you could use them for a multi-user direct sequence spread spectrum system. 3-valued cross correlation. Okay. So it basically gave us several choices for the spreading sequences. And the basic structure was, if A and B are the preferred sequences, then the Gold-Kasami sequences were generated as follows. You take A, keep it fixed, do a modulo 2 addition with all cyclic shifts of B. Then you take the code A itself and the code B itself, and these together gave us 2 to the power of m plus 1 sequences. Okay, and all of them have got very good properties, autocorrelation and cross correlation. Okay. So yesterday we made the observation that Gold-Kasami sequences are nothing but an M sequence scrambled by another M sequence, scrambled by another M sequence. Okay. Would you agree with that? It's an M sequence scrambled by another sequence, or should we qualify it? Or should it be qualified with a specially selected M sequence? It has to be the preferred pair, right? Otherwise it doesn't work for all of them. So it is a specially selected M sequence. So, or basically the preferred pair is what you would have to use. Okay. So in summary, sequences are very important in our study of direct sequence spread spectrum systems. The most important properties that we need to take away or keep at the back of our mind are that sequences, these are going to be used by users to differentiate themselves. So we are interested in 2 properties. One is self-orthogonality, so that you can protect yourself against multipath. Self-orthogonality basically says that if I have a spreading sequence for user X, for one user which is X, this should be as close to a delta function as possible, only at 0 lag. Then you can reject the multipath and then and of course align it with the different multipath and combine. So this self-orthogonality is what helps us against multipath. And the cross correlation or mutual orthogonality is what helps us against multi-user interference. Okay, and today we are going to study both of those, so keep this picture in mind. So this would be across 2 sequences, and we would like this to be as close to 0 for all values of k, and that is what will help us against the multi-user interference. So in summary, this is the key concepts that we want to take away from this discussion: multi-user interference. Okay, multipath also creates interference for us, so it is correct to call it as multipath interference as well. And another key element that we highlighted in the statistical analysis is the following. We said that Rxy of k, when we use correlation based receivers, now this is the leakage from from a unwanted user into your decision statistic. So this is a measure of the multi-user interference. Okay, it is a measure. It represents the multi-user interference component. Measure of the interference caused by other users. So MUI is a and we also said that we are interested, or at least statistically, in characterizing expected value of Rxy of k magnitude squared, because this would represent the interference power. Okay, the total interference that is leaking in addition to your AWGN that is present, this would also cause an impairment to your decision statistic. So this is a representation. Okay. So these are the points that we highlighted, and again, I hope you were able to verify that if we had found the Kasami sequences, let us say D, E, again as two different shifts. So D is one shift of the sequence B and E. I hope you were able to show that RDE of K is 3 valued. Okay, the same 3 values that the preferred sequences satisfy, and this is what we did in the class. I hope you had a chance to verify that, and as an extension, I'd also asked you to check that you could verify that this is equal to -1 over Q. Please do take time to confirm that that is the case. Again, that sort of just helps you gain confidence in the use of sequences. Okay. So that's a broad picture of sequences and their role in spread spectrum systems. Our task today is threefold. One is to look at how does it help us in multipath environment, how to work with it in a multi-user environment, and then of course putting all of them together in a capacity environment. Okay. So multipath environment. So we said that narrowband systems, we can derive something referred to as the equivalent symbol space model. For us, it now becomes a chip space model, and so basically you can have large number of taps, which this is what the channel is, this is what represents the channel. Okay. Now we have to build a receiver that rejects the unwanted parts and pulls out the required signal. So the channel model that we have is R of t with the input signal U of t convolved with this this chip space channel model, which is what gives us this expression, plus the impairment Z of t, where U of t represents the bit that is being transmitted with the spread waveform. G of t represents the spreading waveform. G of t is we are assuming it is uppercase Q chips in duration. GC is the chip waveform. Okay. So this is the framework. A spread spectrum signal has been generated. It is passing through a multipath environment, which is characterized by this chip space channel, which we would now need to build a receiver for. Okay. That's where we are picking up. So the points to note are, we are working with a chip space channel model. Okay. So a chip spaced equivalent channel model, and the original channel we assumed had L plus 1 taps. Now usually when you come up with equivalent models, you don't know ahead of time how many taps that it will be, but we are assuming that L is sufficiently general that it can capture the range of multipath that you are. So the chip spaced equivalent model, you must specify the number of taps. It is an L plus 1 tap equivalent, where L is adjusted based on the number of multipath components. So the number of taps is L plus 1, chip space taps. Okay. The second one is that we will work with a correlation based receiver, and the strength of the correlation based receiver is that it is a match filter, and of course we are working with sequences that have got very good correlation properties, so we want to exploit that. One is the fact that it's a match filter, second one is that it is this correlation properties that will help us be robust against unwanted signals like a multipath or multi-user interference. Okay? So correlation type receiver. It is a match filter, but think in terms of a correlation based implementation, so that way all of the correlation properties, the mutual orthogonality, the self orthogonality, all of that comes into play, and you are always keeping that. So a correlation type receiver is our framework that we are going to be studying. Okay. So yesterday there was a question which I thought was a very important one. I'll make sure that just spend a minute to answer that question. Okay. The question was, supposing I have a symbol that has been spread. So it has been spread by a number of chips. Okay. This is U of t. U of t. Now G of t also has the same span, because U of t, this is the waveform. So when I correlate U of t with G of t, there is a perfect overlap between the waveform that I used at the transmitter and the waveform that I am using at the receiver, G star, let us say. Okay. This is at the transmitter. This is at the transmitter, this is at the receiver. I have a copy of G of t. Whatever comes in the received signal, I correlate. If they're aligned, they're perfect. But what happens in the presence of multipath is that I get shifted versions of U of t. And yesterday's structure that we drew required us to have the following. So that it was a shifted version. Okay. Let us say, take the simple case that it was just shifted by Tc. Then my waveform G star of t is aligned in this fashion. Do you see that? Basically, this is U of t plus Tc. U of t plus Tc, correct? U of t plus Tc. Now, the question that was raised is, this represents bit B1. Then there is, so this represents B1. Then beyond this will be bit B2. Correct? That next bit has already come. So because it's continuous transmission. So this green waveform is now no longer overlapping only with B1, it's also overlapping with B2. So which means that you have to take into account, and that is precisely the problem with multipath, is that when you now have copies of the signal which are going to contribute to your decision statistic. Okay? So how do we why are we not explicitly taking this B2 into account? So in today's discussion, we are going to make the following assumption, that L times Tc, that is the total delay caused by the channel and the multipath, is much less than Q times Tc. That means the total delay is still, so the bulk of the overlap of G star of t is still with the bit B1, and this additional leakage from B2, we are going to sort of say that it is present, but we are not going to, it's going to be small, and a part of the discussion today will clarify this. But yes, it is correct that the bit B2 will now come into play, or if you slide the other direction, bit B0 will start to come into play. So that is the problem with multipath, and that's the reason why you need to have equalization in a narrowband system, and that's why we need to have a special receiver in a spread spectrum system. Okay. So again, good question. So let's pick it up from where we left off yesterday. Don't want to rewrite the whole. So the structure is a tap delay line with L delays of Tc. Each of these branches, keep in mind, is being multiplied by G star of t minus LTC. T minus LTC means G star of t delayed by LTC, and then it is being integrated, because I delayed G star by LTC. my integration limit starts from LTC to LTC plus t. Now, of course, we showed that we can rewrite this as 0 to t and keeping g star of t and not the shifted version. So, if you keep g star of t, then you have to advance r of t. So, basically that is the structure that is easy for us to work with. So, the starting point is this expression 0 to t r of t plus LTC. That means I have advanced it by L times the chip duration, and the equivalent expression was written down. We then multiplied it by g star of t, integrated it from 0 to t. The first term we wrote down, the second term we said we need to write down the expressions for that. That is where we will pick up today's discussion. Okay. So, let us quickly write down the notation and then build on the topic that we have. Okay. So, the values that we want to write down and characterize are as follows. Okay. So, want to define a couple of terms which will help us in our discussion, expressions. RGG of KTC. I am going to define this as follows: integral 0 to t g of t plus KTC. Okay, this is the form of the expression that is coming multiplied by g star of t dt, and then if you go in and write down the expressions for g of t, we find that this particular quantity will depend on this parameter 1 over q equal to 0 to q minus 1 c of q plus k. Okay. So, basically the chip waveform does not really play a big role. It is that underlying chip sequence and its autocorrelation property is what is going to tell you what this value is going to be. But let us write that down, and the other element is that the noise is z of t, the impairment is z of t. So, that will also pass through the correlation receiver, and we will get 0 to t z of t g star, oh no, remember we advanced the received signal, so it should be t plus KTC multiplied by g star of t dt. Okay. So, now using this notation and keeping that previous expression as a reference point, please confirm that you are able to get this value. Y of L, that is the statistic that is coming out from the first branch, is given by HL B times root EB, that is the first term. Then we get a bunch of terms where the waveforms are not fully overlapping. We will write this down as B times root EB summation L is equal to 0 to L minus 1 H subscript L R G G. These are partial overlaps. So, the overlap depends on the different shifts L minus L times TC. Okay. I would encourage you to just write down the start from the previous expression, and for each of the delays write it down in terms of this cross correlation RGG. Okay. And you will of course have the noise term. The noise term passing through the correlation based receiver becomes eta L. Okay. So, as we have expressed. So, this portion represents the desired signal because it has got the expression for what we are looking for. This is a combination of terms which has B in it, but I need to be very careful because the correlation at different lags are going to play a part, and how they combine with H of L is also going to be important. So, I need to be careful with this. So, what we are going to do is that because of this property, okay, these cross correlation values are going to be small by design. So what we are going to do is, that's because of the property of the codes that we are working with. So more or less we are going to say that, it's not worth bothering with the component of B that is present here. I'm going to just ignore this. So basically what is going to happen is, this whole quantity is going to be treated as noise. Okay. So what is the rake receiver doing? It takes the received signal, passes it through a delay chain. Each of those branches, it multiplies by G star of t minus LTC. Basically it's a correlation step followed by the appropriate integration, and then we are looking at y of L, the output of the first branch. And the output of the first branch is what we have written down, has got a very clear contribution of the desired signal and a combination of terms which includes the original noise plus some correlation terms which come from the different correlation at different lags. So this is the expression. That we have. Okay. So what we would like to do is see how best we can work with this expression and quickly converge upon our ability to get the best out of this system. So here is the step that we would like to do. So you can of course encourage you to write it down at least for a couple of more branches. So for the second branch, I'll just write it down for the second branch, and then so second branch we have labeled as y of L minus 1. You will notice that it will give you h of L minus 1 times b root EB, plus it will give you a set of noise terms. It will have all those h coefficients except h of L minus 1, because h of L minus 1 is now in the desired expression. Okay. So if you want to write that down, it will be b times root EB summation L is equal to 0 to uppercase L, but it's not equal to L minus 1, h of L R G G. Now it is L minus 1 minus L times Tc. That's the expression, plus eta L minus 1, because that's the output of the correlator that uses with the appropriate delay. Okay. Now these arguments that are inside this bracket. Okay. Now that just interpret this. If it comes out that the argument is negative, what does that mean? Basically it means 1 over q summation q equal to 0 to q minus 1 c of q, and if the argument is negative, let us say it is some minus j, this means it is c of q minus j. Okay, if it was argument was positive, it will be q plus j minus j, but essentially the behavior does not change. You are looking at a correlation at different lags. You can slide one sequence to the right, or you can slide one sequence to the left. It does not make any difference. So basically it's the same thing. So these terms are all small, and therefore okay. So what is the property that we have used? We have very heavily relied on the self-orthogonality property. Self-orthogonality property. Self-orthogonality property basically says that each of those branches of my rake receiver gives me one term which is very strong in terms of the desired signal. It gives me a combination of terms which is combination of the original noise plus the desired signal, but because of the cross correlation these are suppressed. So self-orthogonality property, again just for reference, we are talking about the fact that RGG of k, we want it to be as close to 0 as close to delta of k as possible, not 0, for k not equal to 0. Okay. Okay. For k not equal to 0. Okay. And that's the so if you have come this far, saying that each of those branches you can write down. First branch, so basically go back to the figure. Here is y of L. Second branch is y of L minus 1. Correspondingly write all the way to the last branch and call that y of 0. Now comes a very interesting step. we say that the final decision statistic will be a sum of all the L branches of a rake receiver, L equal to 0 through uppercase L, HL star times YL, HL star times YL. Okay. Now, go back to the figure and verify YL is being multiplied by HL star, YL minus 1 is H of L minus 1 star, Y0 H0 star. So, basically that is what we have done. If you do that, you can verify that your expressions are going to be given by summation L equal to 0 to uppercase L B times root EB times mod HL squared plus summation L equal to 0 through L HL star of NL. Those are the noise terms that are coming in from the different branches. Okay. So, this is the portion of the desired signal, this is the portion of the impairment. Just for insight, we are going to make one more small approximation. If your autocorrelation properties, self-orthogonality properties are very good, then this NL will actually be equal to eta L, because that will only the noise term will, the rest of it would have gotten suppressed because of the cross correlation properties. Okay, and very important step. If you now have this expression, I can hope you are seeing that this looks like L plus 1 branch diversity. L plus 1 branch diversity, where you have multiple copies of the signal which you have collected together, and of course you have impairment from each of those branches. So, basically if we can make the assumption that all the branches are seeing the same level of interference or impairment, all branches are seeing same level of interference, seeing same level of impairment, okay, then we can do equal gain combining. Equal gain combining is the same as MRC. So, basically then your co-phasing is done only through the conjugation of the channel taps. So, basically MRC is what is optimal in this environment, and we have used, that is what we have done resembles MRC. So, the SNR for my decision statistic comes out to be, what is the signal component and the noise component. So, I will have to square it, b squared, b is plus or minus 1. So, when I take b squared, it becomes 1, root EB becomes EB, and this term becomes summation L equal to 0 through uppercase L mod HL squared. Noise component, the denominator, if it is eta L and the noise variance is N naught, only the AWGN, the multipath interference has been ignored for the moment. Then it's each of those noise terms, eta L is being scaled by HL. So, when I look at the variance, I need to make sure I take into account that the variance will be N naught into summation L equal to 0 mod HL squared. Okay. So, this is going to, by the way, this is the scaling. So, therefore, there should be a square on that. Oh, please, if I miss some of things like that, you should catch it. Okay. So, then simplifying, this one will cancel the exponent. So, this gives me EB by N naught into summation L equal to 0 through L minus 1 mod HL squared. Okay. That looks like gamma naught plus gamma 1 plus gamma L of a L plus 1 branch MRC system, when all of them have equal noise variances, and therefore equal gain combining is the same as MRC. What are the assumptions that we have made? so that we don't forget the assumptions that we have made. What are the assumptions? We have ignored the multipath interference. There is a multipath interference. Assume that if I have perfect self-orthogonality, then this expression is correct. But we will never have perfect self-orthogonality. So therefore, that is one term. What else have we ignored? Well, cross correlation has not come because only one sequence is involved. The remember bit B0, B1, we said that the other bit is not much is coming from there as well. So keep those two assumptions in mind. These are not very limiting in terms of their impact, but we just need to be able to keep that picture in mind. All right. Now just want to bring in a little bit more rigor and insight, because when you look at NL, it is eta L plus a summation that we have to take into account. Let me just write down the expression. So it is B times root EB, B times root EB summation L is equal to 0 to L minus 1 HL RGG L minus L TC. Okay. Okay. Again, I've written it down for the first branch. Basically, these will be the type of noise. This is for branch 1. For branch 1. Okay. Now, one of the important elements that we will need to analyze this very accurately would be to estimate what is expected value of the noise. Okay, that is item number 1, and that you can verify. It's a combination of the noise term plus something which depends on B. Expected value, if you take the noise term, will give you 0, the B has plus minus 1, so that also. So basically, this is a 0 mean, this impairment is 0 mean. Okay. The second component that we need to be careful about is that expected value of NL magnitude squared, the variance. Okay. So the variance expression basically involves us to work with this term. So basically, it will be expected value of eta L squared plus there will be cross terms. The cross terms will have a product of eta L. When you take expression of eta L, the cross terms will go away, and then you will get a square term that is coming in from here. Okay. So you will get EB times expected value of summation L equal to 0 to L minus 1 H of L squared RGG of, I'm just going to write L minus L. The TC I am deliberately ignoring just so that it doesn't. So this is the first term, and you have to multiply it by its conjugate. So I'm changing the variable of summation M is equal to 0 to L minus 1 mod, wait a minute, I think I've written it wrong. This should be only HL. Okay. This is the second term will be HM RGG L minus L, uppercase L minus L with conjugate signs. Okay. And so when we look at this expression, basically you will get the square terms, which will be EB times expected value where L and M are the same. L is equal to 0 through L minus 1 mod H of L squared times RGG L minus L magnitude squared, plus you will get those cross terms. Okay, cross terms are also present. Okay, Now, here is where basically we are trying to get a feel for what is this impairment. We initially said we are going to ignore this this multipath component, right? We just said we are going to ignore it. So what we are trying to do now is sort of get a little bit more insight into what that impairment term is and what is its mean is not a problem. We are looking at the variance. Now, of course, there are these cross terms where you will have H and where L and M are not equal. You need to take those terms into account. Okay. Now, if you sort of take the fact that expected value of HL HM star, if these are they are different tabs of the channel model. So which means that they are not correlated to each other. And if each of those channel taps, if this was a Rayleigh fading channel and you had modeled it, then each of these coefficients will look like they are Rayleigh coefficients themselves. So this one, you know, we are saying, okay, this is not going to contribute a significant portion. So the part that I need to worry about is only where you get magnitude squared. Okay. So then I take the expectation inside. I know that expected value of RGG of L minus L magnitude squared. Okay. This should be approximately 1 over q for my if it was a random sequence or a PN sequence, and most of the time this is the type of cross correlation that we will achieve, self orthogonality that we will achieve. So if you have achieved that level of self orthogonality, then comes the expression that expected value of mod NL squared is the same as N naught, which is the noise variance, plus EB divided by Q summation L is equal to 0 through uppercase L minus 1 mod HL squared. So each of those noise terms, in addition to N naught, has got this quantity. Okay. So what we have done is, we said initially we said, okay, we just said we are going to ignore the multipath components, we are going to take only N naught, and we showed that it is close to MRC. That is correct, that gives us a certain level of insight. But we now are saying let's go in and look at the impairment a little bit more closely. We are saying that the major term is going to come from, major part is going to come from the square terms. The square term basically gives us a contribution of this type. Okay. The most important step comes now. If Q is sufficiently large, if Q is sufficiently large, then everything hangs together, because if Q is sufficiently large compared to L, which is the assumption that we have made right at the beginning, then this whole term kind of drops out, and I can still go back and say, well, you know what, it does look like MRC anyway. My spreading sequence gave me the benefit of suppressing the unwanted multipath related components, and therefore we are actually doing as good as the system, as an MRC. Okay. Now, it is not the same as MRC because these terms have been neglected, right. Please keep in mind that this is the penalty that you have paid, which you have sort of ignored. So it will not achieve the same as full L plus 1 branch MRC, but it will be slightly worse, but it has done a fairly good job. Okay. Two more very interesting observations, which after that we will conclude this discussion. First one, okay, is this a linear system? If you do filtering, it's a linear system, right? It's a linear system. Nothing, no squaring term, nothing which is non-linear. Okay. So if I'm permitted to move the linear parts, I'm going to draw a dotted line around what we consider as a linear operation. Let me do it with the blue line. Okay. These are different for each of the branches. The part that I want to move is the, do I move the, yes. this whole branch is common for each of the branches. So, I can move it to after the summation. So, basically I am going to do the multiplication by G star of T minus LTC followed by the integration, and that means it has been removed from that part. So, this will be LTC to LTC plus T integral dt. Okay? So, invoking the property of an LTI system, I have moved this operation, which is basically this is a filtering operation, right? When you multiply, basically it is like multiplying or convolving with a match filter. So, that you have moved to after the summation, because the filtering is a linear operation, addition is a linear operation, so you can move to the other side. So, then what happens, it is the delay line, follow along, delay line multiplied by HL star, HL minus 1 star, H0 star. Okay? How would you describe that? How would you describe that? It is a matched filter to what?
Channel.
To your channel. Match filter to your channel. Your channel was an L tap, L plus 1 tap delayed. So, what you did was basically you are applying the match filter to your channel model. Okay? Very important observation. So, then this operation, this structure is actually doing the following. When you have moved the filtering operation outside, you can say that you are doing a match filter to your channel model. Time reversed and conjugated is the structure that you are applying. Okay? But match filter requires you to have match filtering to the entire waveform, which means that it is a combination of the chip waveform and the channel. But notice that the match filter to the chip is also present. So, in effect you have done a match filter to the entire chip waveform plus the channel, you have constructed a match filter. So, basically the structure is implementing, so the structure is implementing a match filter to the channel model. The correlation plus the integrator is the correlation based receiver. Correlation based receiver is doing the match filter to the chip based the chip waveform. Correlation based receiver is doing a match filter to the chip waveform. Okay, so, you have a very conventional optimal receiver, and this would be your optimal receiver in AWGN. Okay. Of course, it is not strictly AWGN. What you have done is you have neglected some terms, but very important that this is fairly close to what you would have done in terms of optimal receivers. Okay. Last observation. So, this is one of the things I said there were two things. If you look at this structure, what does it look like? It has got lots of parallel branches which then join together. Okay. Now, if you have done gardening and you want to gather all the leaves, there is a tool which you use which has got a wooden stick, and then it has got certain branches like this. Right? That is what you use to gather the leaves, dried leaves, and that is called a rake. And this one actually looks like a rake, and that is where the name comes from. It is not, there was no person called Mr. Rake who invented this system, because just the structure looks like a garden rake, and therefore it is called a rake receiver. So, in case you are wondering where the rake name comes from, that is where it comes from. Okay. So, that is multipath, how CDMA systems work in the presence of multipath. Okay. What I would like to do is introduce you to the multi-user environment. Again, I was hoping to go a little bit further than today, but again more important that you are comfortable with the material that is being covered, and we are able to cover it at our own pace. So, the first thing that we would like to do is look at what is the difference between a multipath environment and a multi-user environment. Okay. So, multi-user environment is what we would like to develop now. So, multi-user environment is going to have a large number of users, user 1 to user k. Each of them have spread their signals. We will assume that they have different gain terms. We will explain this in a moment, what these terms are. Now, each of these can go through different delays. So, let us call them as tau 1 through delay tau k, okay. And all of these will then get combined into a, we are looking at the uplink of a multi-user CDMA system, okay. Now, each user does not care about the others. It says, okay, I have got my code, I have spread my signal, I have transmitted it. So, in the channel, that is in the wireless channel, all of them are transmitting the same frequency. So, therefore, the channel adds all of them together. So, that is why you get the presence of the multiple users, okay. Now, in addition to this, there will be noise that gets added, that is the noise term, and then at the receiver I must build the receiver that can detect each of these signals. I should be able to detect, because the base station should detect all of them. So, it is a correlation based receiver, okay, because if I want to detect user 1, I need to use a correlation based receiver for okay. So, the channel model that we would like to do is, first of all, we will make the assumption that all the delays have been controlled so that they are all the same. So, this is called a synchronous CDMA system. Synchronous, it is a little bit easier to work with than a asynchronous system, but because the base station controls all the users, you can actually control their timing so that they actually arrive at the same time. So, synchronous CDMA uplink, that is what we are studying, okay. Now, in the presence of flat fading channels, that means there is no multipath, the combined received signal R of t is equal to summation k equal to 1 to uppercase k alpha k uk of t. Uk is the baseband signal representation of each user signal, plus the noise term z of t. Now, what is alpha k? I just want you to take a little bit of time to think about it. Alpha k is a combination of two things. One is, if you did not do any power control, it will be only the channel gain, which will be a Rayleigh coefficient if it was a Rayleigh fading channel, okay. But if you have done power control, which is what you would do in a CDMA system, so this would be the channel gain plus the power control. We have represented it by a single alpha, which is fine, because if it is a flat fading channel anyway, the channel gain would have been a single number. So, this is, so each of these UKs, again you will see a lot of similarities with the previous UKs, can be written as BK times root EB, that is a bit transmitted by each of the users. Each of the users waveform GK of t, and GK of t is the spreading sequence with Q chips, Q is equal to 0 to Q minus 1, C subscript k to denote the spreading sequence of user k times Q GC of t minus QTC, okay. Actually, the multi-user system is very simple, very elegant. We will write it down and then conclude today's lecture. So, if I want to pick up user 1 signal, I do a correlation with respect to user 1. So, a correlation based receiver for user 1 would take the signal R of t and multiply it with G1 star of t, G1 because it's user 1's waveform times dt. If you now write down the expression, what you will find is this will be alpha 1 B1 root EB plus the noise Z1 which is passing through this correlation filter, we will call it as eta 1, and you will have the different other users signals. So, the other user signals are k equal to 2 to uppercase k, those are the user 1 is our desired user. You will get alpha k bk root EB, and you will get a term which depends on the cross correlation between the different users. It will be 0 to t gk of t g1 star of t dt. Okay. This is mutual orthogonality. So, basically the strength of your multi-user performance is going to depend on, so we will denote this as R1 subscript k. That means the cross correlation between user k with user 1's waveform. So, the first term is the desired user and the others are. So, basically this depends on the cross correlation which in turn depends on 1 over q, q equal to 0 through q minus 1, ck of q c1 star of q, that is the chip sequences. Okay. So, this is what we refer to as the multi-user interference. That is the term that comes from, when I do my decision statistic, there is a term which desired signal. This is the desired signal. If there was no one else present in the system, it will be a single user system. That means it will be my desired signal plus the noise term. This is what will be if it was a single user environment. Okay. If it is a multi-user environment, you have this multi-user environment. Okay. So, this is essentially what we have. So, what we now say is, okay, multi-user not a problem, all the users are transmitting, I will build a receiver that detects user 1 and we then find the expression. So, let us call this as the decision statistic y. Now, we would like to understand what are the statistics of the signal component in y and the impairment component in y, and then basically an analysis which is very, very similar to what we have done in the previous case. Okay. And we would like to know what is the, when you look at the impairment, want to know the mean and the variance of the impairment, so then we can statistically characterize. So, again it just requires us to write a couple of steps, but a good place to stop so that you can then go back and see what are some of the similarities between the way we have handled multipath interference and now we are going to do multi-user interference. In fact, even without my input, I am sure you may be able to write down what is the impairment component, its mean and variance. Okay. So, maybe just let me write the answers for you, you can then you can verify that this is indeed the case. So, if I were to look at the noise, the variance of the impairment, it will come out to be N naught plus EB times summation k equal to 2 to uppercase k mod alpha k squared expected value of R1k magnitude squared. Okay. And since we know that this for the case of the PN sequence, PN codes will be approximately 1 by q, it starts to look very similar to what you encountered in the multi-path case. And basically we will follow the very similar step. If you can try this, but I will pick it up from this expression for y and then derive the impairment variance. Okay. Thank you.